Okay, guys, now we're going to do an example using the linear charge distribution, or using a linear charge distribution to calculate the electric field. This is associated with reading 2.1.4. It's also very similar to example 2.2. And I want you guys to be able to set up and solve an integral for a linear charge distribution, and this will help you with other nonlinear charge distributions as well, hopefully. And I want to show you guys how you can check your answer using both limits and by checking the units or doing something called dimensional analysis. Okay, so let's get started. The problem that we're going to solve is the same problem in your book as 2.3, so I'll just write it out here quickly. The problem is I want to know what the electric field is at a point above the bottom of a uniform, okay, I'm going to underline that word, charged rod, okay. No, I guess I could put an is there. What is the electric field at a point above the bottom of a uniform charged rod? And I know that the rod has a length of L and a uniform charge density of lambda. Okay, again, if you look in your book, this is the same as problem 2.3. All right. So this is the problem I want to solve. The first thing I want to do, not so different than introductory physics or other physics classes, right? I've got an actual object here, and I want to figure out the electric field at a particular point. So it makes sense to draw a picture, okay? So the first thing I'm going to do, my first step here is to draw a picture of the situation. Okay, so I'm going to go ahead and draw it like this. It doesn't really matter the direction you draw this rod, whether you draw it vertical or horizontal. You should get the same answer. But there's my rod, okay? And then I want to identify the point where I'm trying to find the electric field. And in this case, I'm trying to find the electric field at a point above the bottom. So that's my point there. I'll draw the P below. Okay, so that's where I'm trying to evaluate my electric field. Okay, I'm going to go ahead and help myself out and define a few more things. I know that the length of this rod is L. All right, and I'm going to draw a coordinate system. Okay, and for this problem, a nice two-dimensional coordinate system with the origin at the bottom of the rod here makes a lot of sense. That's going to simplify what I'm trying to do. Okay, what I'm going to be solving here is, I mean, it's been pretty obvious so far that this is going to be a linear charge distribution, but how do you know that? Well, all of the charge is oriented along a line, even though it's a rod, which in real life has some dimensionality to it. We're given a linear charge distribution, so that means the amount of charge along the rod is what's defined. So this is going to be a problem where I use that integral that I just derived. So I know that this is a linear charge distribution. That's what I'm given. And so I'm going to start with the integral for the electric field that's appropriate for a linear charge distribution, okay? And that's this guy right here, okay? So I'm going to write that out just like it looks in the book to start. Okay. And now I need to transform the integral. Basically, I've got this thing, okay, and I need to figure out how to solve this integral with this picture here. Okay, so the first step to do that, it's helpful to go ahead and draw some of these relevant things in the integral in your picture. And by that, you want to, just like we did when we derived that integral, come up with just a little portion of your object, okay, that you can call, you know, your little infinitesimal length, which you are going to calculate the electric field from and then integrate over the rod. Okay, so I've got my dl here. Okay, that's defined there. I need to figure out what my separation vector looks like. Remember, that's always going to point, okay, from the source charge, in this case it's this little chunk of the rod, to the point. And that's going to look like that. Okay, so that's my separation vector. Okay, and then if I want, I can also go ahead and draw the position vectors that show up in this integral. So I've got a position vector for the point where I'm actually calculating the electric field. That's just going to be the r. Okay, that's kind of like where my test charge was when I was talking about Coulomb's law. And then I've got my position vector for the point where the source charge is. And if you remember, that is r prime. Okay, so if I look at my picture here, I've defined some of the things here that are showing up in my integral. All right, so now we're going to transform the integral, and that means, okay, I'm going to use my coordinate system here. I've defined a Cartesian coordinate system. That makes sense for this problem because this rod is falling along the y-axis, and I can use this Cartesian coordinate system, okay, to rewrite this integral or transform this integral into something that I can actually solve. Okay, so let's think about this and be a little clever. So I'm just going to take the different parts of my integral here, and I'm going to rewrite how I can treat them in this problem. In this case, because it tells me that the charge distribution is uniform, that means that this is just a constant. So I'm just going to take out the, I should have a prime on it, by the way, the r prime dependence, and just rewrite that as lambda. And that's because this is constant and also uniform. All right. Now let's think about this dl prime. This is a little chunk of my rod here, and this is what I'm going to integrate over to basically calculate the electric field from this whole rod, right? This is what I'm integrating over. Well, according to how I drew this picture, dl is really just a little chunk of position in the y direction, right? It's just a little chunk of position in the y direction. And that's because the way I drew the picture, okay, the rod is along the y-axis, okay? And I made my life simple by doing that, okay? If I had put the rod this way, then this would be a dx. If I had drawn the rod off at some angle, man, I would have made this integral a lot harder than it needed to be, okay? R, that's the position where I'm trying to calculate the electric field. For my problem, it doesn't tell me exactly where P is, but I know that P is along the x direction, and I'm going to end up with an answer that tells me what the electric field is anywhere along that x-axis. So I know that I can define this R, which is the position of my point P, as some x, okay, depending on where it is along that x-axis, how far it is away from the rod, but it doesn't have any position in the y space or z space. So just x, 0, 0. And again, that is because P is on the x-axis. Okay, let's keep going. This R prime, that's the position of that little chunk of the rod that I am calculating the electric field of. Because the rod is along the y-axis, the position vector for that little chunk is going to just be y, wherever it is along the y-axis. Okay, so this gives me a vector, okay, that points to dl. Okay, go ahead and do this bit here. This is the magnitude, or the magnitude squared, of my position vector. That is just going to be here. Okay, if I look here, the way that's drawn, that's the length of this vector. That's going to be x squared plus y squared. That's the length of it. Then I'm going to square it again. Okay, so that part is going to just be x squared plus y squared. Okay, and then the last little bit, I've got my script r hat, that unit vector. If you guys remember, that's going to be equal to my separation vector divided by the magnitude of my separation vector. So if I look here, my separation vector, let's draw it here. Okay, it's got a component in the x direction that's just x, right? That's the x component. The component in the y direction is negative y. Okay, so this is the x component. This is the y component. So if I write my separation vector in component form, it's going to look like x, negative y, 0. Okay, and then the magnitude of that is x squared plus y squared. And then I need to take the square root of that, so to the 1/2. Okay, so basically what I've done is I've recast the parts of this integral, taking into consideration the picture that I drew here and using Cartesian coordinates, which are going to allow me to do this integral a little bit easier. Okay, so let's use this to rewrite the integral. Okay, so we're going to rewrite that integral using what I just wrote out. Okay, so that means what I'm doing here is I am calculating the electric field at my point R, but now my point R is just somewhere along the x direction. Okay, I'm going to keep this bit in there. That doesn't go anywhere. Okay, I still have lambda, but now lambda is just a constant, so I can just write it like that. Okay, and then that's the magnitude of the separation vector squared. That turned into x squared plus y squared. Okay, and then my r script r hat, that unit vector, turned into this bit here. Okay, and then the dl is now a dy. Okay, and just remember here, this bit, this is a vector, okay? So we're still, the electric field is a vector, so the integral on the right-hand side here needs to give us a vector, okay? And the vector here, right, this would be equal to x, x hat, or a unit vector in the x direction minus y, y hat, okay, plus 0, z hat. Okay, so this is the part here that turns this whole integral into a vector. So I'm calculating a vector electric field. Okay, so let's think about that a little bit more. We got to do this piece by piece, okay? So in general, right, we are calculating, if we're doing it in 3 dimensions in Cartesian coordinates, we are calculating a vector electric field that would look something like this. Okay, Each of these can be solved. Okay, each can be found, okay, by solving one component of the integral. We're just going to do one here. You can do another one for fun, okay? We're going to do the x component. So let's do the x component. All right, so the x component of this integral, so just the magnitude of the electric field in the x direction, that's just going to be equal to 1 over 4 pi epsilon naught times the integral lambda. Okay, I'm going to simplify this a little bit. This will be 3/2. And then we're going to get just an x up here and a dy. Okay, so we just get the x because we're just taking the x component of this integral. Okay, and then we combine these two terms to get this. All right. Now we just need to figure out what are the limits. Okay, so what are the limits of our integral? Well, to figure that out, let's look back here at our picture. Okay, so I'm going to cheat a little bit. I'm going to copy this picture, throw it back over on this slide. We'll put it over here. Technology. Okay, if I look at our picture, I want to integrate all of the charge along this rod. Okay, that's what this dy represents. So the rod starts at y equals L and it ends here at y equals 0. Okay, so I know that the charge extends from y equals 0 to y equals L. Okay, so that means I can throw integration limits on here. I'm going to go from L to 0. All right, so now the only thing we have to do is this integral here, okay? And maybe to simplify it, I can rewrite it one more time. And I'm going to pull out all of the stuff, okay, that doesn't depend on y. Remember, if something doesn't depend on what you're integrating over here, in this case y, you can pull it out of the integral. So lambda is a constant. It doesn't depend on y. X here does not depend on y. I can't pull out anything here because this is an expression that does depend on y. So if I want to simplify this, I can, like that. Okay, and then I'm left with 1 over x squared plus y squared to the 3/2 dy. All right, so now basically we're in a situation where it's kind of like a math class. There's different ways to solve this integral. Okay, you can solve it by substitution. You could look it up in an integral table. That's okay. Or you can use Mathematica. Okay. In this case, we're just going to skip to the solution. At the end of the video, I'll go back and show you how to do this integral. But I want to get to the point here. Let's skip to the solution. So let's say you took the easiest method and you looked up this integral in an integral table. Okay. And what you got was that the electric field in the x direction is equal to lambda over 4 pi epsilon naught. It's 1 over x, y over x squared plus y squared to the 1/2. And that goes from y equals L to y equals 0. Okay, so that gives you the final solution here, 4 pi epsilon naught. 4 pi epsilon naught times y equals 0 to the 1/2 to the 1/2. Woo! Okay. Are you done? Are you done with this problem? No, not in this class, okay? You need to check it. You need to check it. It's just too easy to make a mistake when you're doing math this complicated. All right. So how do we check to make sure that this is right, or at least it's not obviously wrong? Well, our first method is going to be checking the units, also known as dimensional analysis. Okay, let's just start out by writing out some of the units of the components of these things. The charge density, if I assume standard units, is going to be coulombs over meters. Epsilon naught, again assuming standard units, is going to give me coulombs squared over meters squared over newtons. X and L, those are both lengths, so I'm going to assume SI unit of meters. And then the answer, which is an electric field, should have units of newtons over coulombs, okay? So let's go ahead and take this expression that I just solved for and figure out what the units are. Paste that down here. Okay, so the units of this whole guy here, taking it term by term, the first thing's going to give me, let's see, I'll just write it out. Coulombs over meters, okay, and then I'm going to get the 1 over the units of the epsilon naught. I'm going to get 1 over x, which is going to give me 1 over meters. And then I'm going to get meters over meters again. Okay, so let's just cancel those units out. These 2 meters are going to cancel. All of these meters are going to cancel. One of these is going to cancel. One of those is going to cancel. And indeed, I'm going to end up with the correct units of newtons over coulombs. Okay, good. So my unit check worked out. Okay, I did get appropriate units for the electric field in SI units. Okay, my second method for checking the answer is going to involve taking limits. Okay, so I'm going to take my expression and I'm going to take some variable, either to a really big number or to a really small number like 0, and I'm going to see if the equation transforms to the expected value. All right, so what is the expected value? Well, let's think about it. We've got a rod of charge. Okay, we got a rod of charge here. We've got some point P. Okay, what would you expect if, would you expect that x component to be if we moved P really far away? Okay, well, think about it. If we moved P really far away, or we said that the x here, which is this position, is much, much greater than L, okay, then our rod should start looking like a point charge. Okay, so the rod should look more like a point charge. All right, so let's go ahead and do that. Here's our expression for the electric field in the x direction at point P. Okay, if I take x much, much greater than L, okay, then we get x squared plus L squared to the 1/2. That's basically going to look like x. Okay, or I could factor x out, and then I could write the term this way. Okay, I do that because if I look at this expression, this one, and if I take x to infinity, this whole expression is going to go to infinity. I think it makes sense that it goes to x if this term is much, much bigger than this, but if I think about taking the limit as x goes to infinity, this whole term goes to infinity. If I just think about taking the limit of x goes to infinity of this term here, then I get x here. Okay, so sometimes it's helpful to factor x out. That just makes it more mathematically meaningful. Okay, so e to the x, so in the limit of x is much, much greater than L, e to the x, x goes to lambda over 4 pi epsilon naught, 1 over x squared. Okay, remembering that x times L, sorry, this should be an L here. X times L, that is equal to Q, the total charge of the object. X in this particular scenario is about the same thing as R. So what you end up with is Coulomb's law, or the electric field, for a point charge, which is what you would expect. Okay, so that's also a good check. So the limit works. If I really wanted to find the full electric field at that point, okay, so to find the vector, right, electric field, you have to go back and solve for y, for the y component. Okay, and then you would have the full field because the E would be equal to E to X, the X hat direction, plus E Y in the Y hat direction. Okay, I recommend you do it for fun. Okay, why not?